This section is about the applications of normal distributions. Last section we talked about finding areas underneath a standard normal. Now we're going to talk about finding areas under any normal curve. You always want to draw a normal curve first when you're dealing with these types of normal distribution problems. Of course, we're going to use that normal CDF just like in the last section. And then write a complete sentence interpreting the value found in step 2. Example 1. IQ scores can be modeled by normal distribution. There we go. We have a normal distribution with a mean of 100 and a standard deviation of 15. What is the probability that a randomly selected individual has an IQ between 80 and 125? So like I mentioned before, we always want to draw a bell-shaped curve when dealing with normal distributions. Okay, you don't want to retain a lot of this information in your head. You want to draw pictures. Okay, always identify the center here, the mean. In this case, it's 100. Now, I wouldn't add and subtract off the standard deviation here. The reason being is that it can get very cluttered. Okay. Now, what is the actual question asking for? The probability, again, that's the area, that a randomly selected individual has an IQ between 80 and 125. Okay, well, here's 100. 80 would be somewhere to the left of it. 125 is a little bit further than 80, right? And we're looking for that area, okay, that shaded region. When finding areas underneath a normal distribution, we're using normal CDF. Okay, we have our lower, upper, mean, and standard deviation. Now in this case, the mean and standard deviation are not 0, 1. There are actually given to us 115. So our lower bound in this case is 80. Upper is 125. The mean is 100. And the standard deviation is 15. Let's run that through our calculator, at least once for this section. All right, let's start with the fresh, clear home screen. And in order to find this normal CDF function, we have to do second vars. Go to normal CDF, that second one. We're never going to use normal PDF in this class. Lower, upper, mean, and standard deviation. Now, if your calculator doesn't have this output, you might have an older 84 or a TI 83. Then you're going to just put it in the way you see it on my screen here. All the values separated by commas. Okay, so I have an 80, 125. The mean is 100, and the standard deviation is 15. Put that on correctly. Press enter, and we get 0.8609. If we round to 4 decimal places, we get 0.8610. Find the percentile ranking of an individual whose IQ is 132. So it's the same problem, but this time they're asking something slightly different. All right, let's draw a fresh bell-shaped curve here. It's the same problem, so we're dealing with the same mean of 100. So someone who has an IQ score of 132, well, 100 is at the center. 132 would be somewhere up around here, I would say. And what they mean about percentile, well, percentile is the area to the left of this, okay? So the area to the left, okay? If you were to say, for example, you're the 90th percentile, that means you are in the top 10%, right? That means 90% of everybody has a lower IQ score than you, okay? So again, that's not the answer for this question. We'll find it right now, but let's find that using the normal CDF. We have the lower, upper, mean, standard deviation. Okay, lower. There's no bound to this left side, right? It goes all the way to negative infinity, so that's negative E99. Upper, well, upper would be, well, all the way up to 132. The mean is 100. And again, the standard deviation is the same as it was before, 15. Okay, if we run that through our calculator and round to 4 decimal places, we will get 0.9836. Okay, the interpretation there would be an IQ score of 132 is the 98th percentile when rounded. All right, example 2. The National Collegiate Athletic Association, NCAA, requires Division I athletes to score at least 820 on the combined math and verbal SAT exam to compete in their first college year. The SAT scores of 2015 in California were approximately normal, with mean 1,010 and standard deviation of 209. What proportion of all students in California who take the SAT would be NCAA qualifiers? Source, College Board. Okay, again, we're dealing with an approximately normal distribution. So let's go ahead and draw the picture here. All right, let's go ahead and identify the center here. In our case, the mean is 1,010 with the standard deviation of 209. Let's just go ahead and label the mean here. Okay. Now, what was the question here? It said, what proportion of students who take the SAT would be NCAA qualifiers? Well, what does it take to be NCAA qualifier? Well, up here it says it takes at least a score of 820. Okay, so where's 820? Well, here's 1,010. 820 should be to the left of that. And they're trying to qualify, right? So at least 120. So can you score less than 120? No, you have to score more. So 820 or more. That's what that means. So this will give the proportion of those who would be NCAA qualifiers, right? All right, let's see. We find areas underneath a normal distribution using normal CDF. Lower, upper, mean, standard deviation. Our lower bound in this case is 820. Or upper, well, it goes all the way up to positive infinity. So we use E99. The mean 1,010 and standard deviation 209. If we run that through our calculator, we get 0.8183. So we say that about, if we're writing this in percentage, about 81.83% of students would be NCAA qualifiers. Okay, so now we've dealt with finding areas underneath the normal distribution, but what if we already know the area and we're trying to figure out the value that splits the normal distribution into two parts? Okay, well, we're going to be using something called the inverse normal for that. Okay, and that's also in your calculator under the distribution menu. It's going to be inverse normal, and the inputs here for that function is area to the left, the mean, and the standard deviation. Example 3. Find the following z-scores given the following areas. Show what your input is in your calculator. Okay, so for z-scores, we know that we're dealing with standard normal, which means mean is 0 and standard deviation is 1. Sorry, so let's keep that in mind. Find the z-scores such that the area underneath the standard normal curve to the left is 0.2. Again, we're dealing with a standard normal curve, so we want to draw a picture here. Okay, the center is, in this case for a standard normal, it's 0. Now, they're asking a slightly different question. They're already giving us that the area is 0.2. So there's some specific number somewhere along this line such that the area to the left is 0.2. So you think of that as like 20%, right? Now, I know 0 splits this distribution into 50% and 50%. So where would it be where the cutoff is that 20% is to the left and then the remaining portion is to the right? Well, I would say that if you place something down here, it looks like this area would be about 20%. And then the remaining portion, well, what's the remaining portion? Well, everything has to add up to be 1, so the remaining portion has to be what? 0.80? Okay, this mystery number that we're trying to find, well, that's found using this inverse normal function. Inverse normal. All right, so the first input is the left area. The second input is the mean. and then the standard deviation. So there's only 3 inputs for this. In this case, the area to the left of this partition is 0.20. The mean, again, this is a standard normal, so we have 0. Standard deviation, 1. Okay. If we calculate that, well, let me show you how to do that on the calculator. So on your calculator, just make sure that you're on a fresh, clear home screen. Go to second distribution. Go down to inverse normal. In this case, it's the third one. Now again, if you don't have this interface right here, then just go ahead and put it into your calculator the way you see it on my screen right here, where you do 0.20, comma, 0, comma, 1. For the rest of us, they're asking for the area to the left. It doesn't specify left, but that is what they want. That's 0.2. Mean is 0, standard deviation is 1. Press enter, and we get a negative number. Well, it does make sense because anything to the left of 0 should be negative. Part B, find the z-score such that the area under the standard normal curve to the right is 0.35. All right, so same thing as before. Let's go ahead and draw our bell shape here. We have the 0 at the center because it's a standard normal. And we're looking for something in which the area to the right of it would be 35%. So we're looking for the area to the right. All right, so for me, it looks like if you were to partition this somewhere around here, some value, some mystery number that we don't know, cut this up, wouldn't the area to the right of this, doesn't that kind of look like it's 35%, roughly? What would be the remaining portion to the left-hand side? Well, 1 minus 0.35, 1 minus 0.35 is equal to 0.65. Right? So that means this portion here is 0.65. In order to find this value that partitions this standard normal into 2 parts, the left side being 0.65 and the right hand side being 0.35, is found by using inverse normal. We have the left area, and then we have the mean and the standard deviation. Again, the area to the left in this case, we did have to calculate it, which is 0.65. The mean here is 0, and the standard deviation is 1. Again, because we're dealing with the standard normal. If you were to run this through your calculator, you would get 0.39. And it does make sense that it's a positive number because it is to the right of 0. And C, find the z-scores that separate the middle 70%. Okay, so this is kind of interesting. Let's find the bell-shaped curve here. And we're looking for the middle 70%. Okay. Again, since we're dealing with a standard normal, we have a 0 at the center, right? And we're looking for 2 partitions that will make up the middle 70%. Okay, so they are going to be symmetrical. So this middle portion is 70%, and there's 2 mystery numbers. Okay. Now what's left over from when you subtract 0.70 from 1? Well, you're left with 0.30, right? And if that's 0.30 that's left over, evenly split into 2 tails, then doesn't that make sense that this should be 0.15? Again, if you were to add up all these regions, 0.15 plus 0.70 plus 0.15, they should add up to 1, which they do. All right. Now let's go ahead and calculate these values. Inverse normal. This one also, inverse normal. Okay, so let's start with this left one. Inverse normal. We have the left area, the mean, standard deviation. All right, the area to the left of this, well, it's 0.15. The mean being 0, and standard deviation is 1. Now, if we run that through our calculator, we get negative 1.04. Okay, that's negative 1.04. Now this other one over here, you got to be a little careful. Okay, the most common thing people would write here would be, oh, the area to the left is 0.70, but that's not true. The area to the left is 0.70 plus an additional 0.15, right? 0.70 and the 0.15. So we have to add those up to be 0.85. Okay, then the mean again is 0, standard deviation is 1. Okay. if you were to run that through your calculator, you would actually get a positive 1.04. Okay. Now that only happened because of the symmetry, because 0 is at the center. But if the mean was anything other than 0, then you don't expect these to be opposites of each other. Example 4. A statistics instructor obtains heights over students. Luckily, the heights are normally distributed. Okay. That's good to know. With a mean of 64 inches and a standard deviation of 4.6 inches. Find the height for one of her students at the 75th percentile. That is, find the height that separates the bottom 75% and the top 25%. Again, we're dealing with a normal distribution, so we always have to draw a normal distribution curve. Right? Identify the center, which in this case is the mean, and our mean here is 64. Okay, what's the question asking? It's asking, find the height that separates the bottom 75 and the top 25. Well, the bottom 75. Well, the 64 separates the bottom 50 and the top 50. So the bottom 75, well, that should be somewhere around here, right? Some mystery number that we don't know separates the bottom 75% and the top 25%. All right. In order to find that number, we have to use inverse normal. Left area, mean, standard deviation. Area to the left in this case is 0.75. The mean, they told us it was 64, and the standard deviation is 4.6. Okay, if we run that through our calculator, and let's go ahead and just round to one more decimal place. So we get something like 67.1. Okay, and that makes sense because 64 was a mean. We know that the 75th percentile was going to be greater than the mean. Example 5. It is known that the length of a certain steel rod is normally distributed with a mean of 100 centimeters and a standard deviation of 0.45 centimeters. Okay, so it's a pretty small standard deviation. Suppose a manufacturer wants to accept 90% of all rods manufactured. Determine the length of the rods that make up the middle 90% of all steel rods. Okay, so this is very similar to the problem that we just did a couple of exercises ago. We're dealing with the normal distribution, right? So we're going to go ahead and draw that bell-shaped curve. Let's identify the center, the mean. In this case, it's 100. And we're being asked to find the length of the two rods that would make up the middle 90%. Okay, so the cutoffs. So we're looking for the bottom cutoff and the upper cutoff. Okay. Now in manufacturing, what they would say is they're accepting the middle 90%, and the remaining portions they're probably just gonna toss them away, throw them away, maybe remelt them, and create new rods, right? So the middle 90%, right? Subtract that from 1, we're left with 10%. And because of the symmetry, that means there's 5 in each tail. There's 5% here and 5% here. Okay, let's figure out what those numbers are. So in this case, that's found by using inverse normal. Left area. Why is it left area? That's just the way that your calculator was programmed. They could have gone with the right area, but they decided with the left area. Mean, standard deviation. Left area, well, the left area to this is 0.05. The mean was 100, and he told us that the standard deviation was what? 0.45. Okay. And let's go ahead and calculate this, and let's come up with 2 decimal places. They give us the standard deviation in 2 decimal places, so let's just go ahead and answer this with 2 decimal places. If you run this through your calculator, we get 99.26. Okay, that does make sense because it's less than 100. Now for the right one, inverse normal, well, we're going to have the left area, the mean, and the standard deviation. Well, the area to the left of this, again, just like the previous problem, it'll be 0.90, right, plus 0.05, which adds up to 0.95. Then we have the mean, again, it's the same as before, 100, and the standard deviation of 0.45. If we run that through our calculator, we get 100.74. And that does make sense because it is more than 100. So they're going to throw away anything that's lower than 99.26 centimeters or anything greater than 100.74 centimeters because they would be either too small or too large. All right, last example. The scores earned on the mathematics portion of the SAT, a college entrance exam, are approximately normally distributed. Okay, that's good to know. The mean is 516 and the standard deviation is 116. What score should a student obtain in order to be in the top 3%? Okay, so if they're in the top 3%, then they did better than the bottom 97%, correct? All right, so let's keep that in mind. Let's draw a bell-shaped curve. So identify the mean here. In this case, it's 516. Now, to be in the top 3%, that means you did better than the bottom 97%. So that means your score should be somewhere around here, right? The bottom would be 97, and this would be 0.03. All right. Calculate this using inverse normal. You have your left area, your mean, and your standard deviation. The area to the left of this partition is 0.97. The mean in this case is 516, and the standard deviation, which is 116. If you were to run this through your calculator, you would get 734.2 would be the score in order to be in the top 3%.